to the lecture series on differential equations for undergraduate students. Today's lecture is on Fourier integrals. In some last lectures we had seen that Fourier series are very important tool in solving many practical problems involving periodic functions. Let us try to extend this idea to non-periodic functions as well, because in many practical problems we have functions which are not periodic. So, let us try it to extend this in this one, and let us first see with the help of example. Consider the periodic square wave FLX as 0 from minus L to minus 1, 1 from minus 1 to 1 and 0 from 1 to L. So, certainly we want that this period 2L has to be greater than 2, since we want from minus 1 to plus 1 it should be 1 and after that it should be 0, and we want its periodic with period 2L. So, FLX plus 2L should be equal to FLX for all x. Let us see how this function looks like, why we are calling a square wave. So, if I take L is equal to 2, that means period 2L would be 4 and the function would be 0 from minus 2 to minus 1, then 1 from minus 1 to plus 1 and then again 0 from 1 to 2, and we are making it periodic from Fx plus 4 is equal to Fx, that is we are just moving here, after that here from minus 2 to plus 2 and then again we are repeating. So, whatever the function over here we are repeating like this. So, we are getting is this is square waves. Now, if I extend this L to 3, we would get again that from minus 3 to minus 1 0, 1 to plus 1 it would be plus 1 and then 1 to 3 it is 0. Again now the period is 6. So, we would repeat it after that one. So, we are getting the squares a little farther. Again if I take L is equal to 4, it would be like this. So, if I move on like this, we would be getting is that these squares would be recurring at a more and more distances. Let us see if I take L to be very large, that is take the limit as L approaches to infinity of this function. That says is I would get the function 1 in minus 1 to plus 1 and 0, otherwise because L we are approaching to the infinity. So, from minus infinity to minus 1 it would be 0 and from 1 to infinity it would be 0. What this function would look like? 1 square in between from minus 1 to plus 1 and 0 elsewhere. Now, let us see this we have said is that is FLX is a periodic function. Now, let us see how this Fourier series of this function FLX will behave when we increase L or we change the L. So, let us see first for the Fourier series for FLX. This is FLX which is 1 in minus 1 to plus 1 and 0 from minus L to minus 1 and 0 from 1 to L, and then periodic with Fx plus 2L as FLX. Find out what is the Fourier coefficients, that is using the Euler's formula. A naught L, L I am using, that is we are using this particular L, 1 upon 2L minus 1 to plus 1 dx, because the function is 0 from minus L to minus 1 and 0 from 1 to L. So, we do have 1 only in the interval minus 1 to plus 1, which is nothing but 1 by L, and what will be an would be nothing but 1 upon L integral minus 1 to plus 1 cos n pi x by L dx, because the function Fx is 1 in the interval minus 1 to plus 1. What will be this integral? This is an even function, we can write as 2 times. So, 2 by L 0 to 1 cos n pi x over L dx, its integral is nothing but the sin n pi x by L divided by n pi by L, evaluated from 0 to 1 we would get finally as 2 by L sin n pi by L upon sin n pi by L. Now, what will be the coefficient Bn? Bnl would be integral 1 upon L minus 1 to plus 1 sin n pi x over L dx. Now, you see this function is odd function in this one. So, this should be integral should be 0. So, we are getting finally Fourier cosine series for this function. And what will be its amplitude? Because Bn is 0, we would get the mod of a n, that is square root of the an square plus bn square, n square, bn is 0. So, n square only square root we do take only positive quantity. So, it would be 2 upon n pi sine n pi by L. Now, if I just plot this one, this is called the Fourier amplitude spectrum. Let us see this curve. First we have taken that 2L is 4. So, the waveforms are closer enough. This kind of function we were having. If I plot its amplitude spectra, that means I am plotting a n L versus n pi L. A n L was 2 upon n pi mod of sine n pi by L. Now, when L is equal to here 2. So, what we would be having is 2 upon pi sine n pi by 2. Now, when n is 1, sine pi by 2 is 1, what I would get amplitude as 2 upon pi, and here we are plotting it with n pi by L, that is here n is 1, that is pi by 2, at pi by 2 I am plotting it here. Like this is being plotted. So, when n is equal to 3, it would be more or less 1 and like that. Now, we see in this graph we are getting this wave, then it is going down, then it is coming up. So, we call it half wave. In each half wave I am having one maximum amplitude. Let us see when L is equal to 4, that is my period is now 8. This would be the function type. Now, if I am plotting this one, the maximum value which we would be going for n is equal to 2 here, that would be here, because n is equal to 1, we would be taking it pi by 4, like that. We just come here, this is value is less than your 0.5. In the first one it was less than 0.8, now here it is less than 0.5, and in half wave I am having 3 amplitudes for each one, like that we are going on. Now, if I take L is equal to 16, of course here next one has not been plotted, it would be little bit far away. We do get this kind of one, and the maximum value we are getting is less than 0.25. Now, what we are seeing in all these graphs, where I am plotting these amplitude versus this omega n, we would call n pi by L as omega n. We are getting is that as we are increasing my L, our amplitudes are coming more and more in half wave, that is they are becoming dense. Moreover, their value or this is length is decreasing. So, what we say is that if I increase my L, I would get that this will become more dense, we will have in half wave many of them, and the length that will decrease and it will reach to the 0. What now, what is conclusion we are going to draw from here? Let us see. From here we would come to this one, representation of a function as Fourier integral. That is, till now rather than having a sum, that is Fourier series, the series we would be changing to the integral. How we are going to do it? We will take the help of the just now whatever we had learned from the graphs. So, let us see that is mathematically how we are going to do it. Fourier series for function f(l(x) would be a naught, summation n is running from 1 to infinity, a n cos omega n x plus b n sin omega n x, where omega n of course I am writing n pi by L, that is rather than writing here as cos n pi by L x, like that we are writing here. Now, substitute this a naught, a n and b n by the Euler's formula. For that one more thing we would be assuming over here, that as L is approaching to infinity, f(l(x) is approaching to f(x). f(x), if you do remember, we had find out the function is 1 in the interval -1 to +1 and 0 elsewhere, that was the limit. Moreover, we would be assuming is that wherever is required, all the integrals and the series convergence is existing, that is the sum of the series and the integrals are existing. Moreover, we would be assuming certain places, that is they can be interchanged, that is the summation and integration signs can be interchanged. For that, if you remember, you have done uniform convergence and that kind of results. So, those results we would be assuming here as they are happening. So, let us see. Now, A naught is 1 upon 2 L minus L2 plus L FLT dt. I am changing this function x to t in the integral, because I am saying is that FLX is being represented at x. So, all the integrals and integrand we would be changing it to the t, so that there is no confusion between the integrand and the value at the point at which the function we are evaluating. Plus 1 by L, summation n is running from 1 to infinity cos omega n x, a n is 1 upon L that we have taken outside, integral minus L to plus L FLT cos omega n t dt, and plus sin omega n x integral minus L to plus L FLT sin omega n t dt. That is, all these coefficients a naught, a n and b n, we had replaced them by Euler's formulae. A naught this one, for a n 1 upon L this one, and for b n 1 upon L times this one. Let us see some delta omega. This we are saying is omega n plus 1 minus omega n. Omega n is n pi over L, that says is it would be pi by L. Now, if L is approaching to infinity, pi by L would be approaching to 0, that is delta omega would be approaching to 0. Moreover, 1 upon L we could write as delta omega upon pi. So, FLX I can write as 1 upon 2L minus L2 plus L FLT dt plus delta omega upon pi, 1 upon L we are changing into delta omega upon pi, summation n is running from 1 to infinity cos omega n x integral minus L2 plus L FLT cos omega n t dt plus sin omega n x integral minus L2 plus L FLT sin omega n t dt. Now, take the limit on both the sides. So, as L approaches to infinity, we do know that FLX approaches to Fx, and as L approaches to infinity, integral 1 upon 2L minus L2 plus L actually Fx dx minus infinity to plus infinity Fx dx, this is 0. Then Fx, so now I am taking the limit on both the sides. So, FLX is approaching to Fx, this where it would be, this integral would be 0. I would be getting is delta omega upon pi, summation n is running from 1 to infinity cos omega n x integral minus infinity to plus infinity ft cos omega n t dt plus sin omega n x integral minus infinity to plus infinity ft sin omega n t dt. Now, what assumptions we have taken over here? We see here we have taken FLX is approaching to Fx. So, wherever we were having is FLT, that is approaching to Ft. We had assumed that all the limits, integrals and the summations, they are existing. Moreover, the interchange is possible. What it says is that if I take the limit over here, then I can interchange this limit with the summation sign. So, the limit I am taking inside, limit is with respect to L, I am changing it, that is the integral minus infinity to plus infinity. Moreover, the limit FLT is being also changed with Ft. So, all those assumptions on the limit, integrals and summations we had assumed over here. So, finally, we have got Fx we can approximate as delta omega upon pi, summation n is running from 1 to infinity cos omega n x integral minus infinity plus infinity Ft cos omega n t dt plus sin omega n x integral minus infinity to plus infinity Ft sin omega n t dt. So, Fx, now delta omega I am taking inside, the summation sign is also inside 1 upon pi. Now, rewriting the same term, summation n is running from 1 to infinity delta omega times cos omega n x and then this integral minus infinity to plus infinity Ft cos omega n t dt, and again this breaking this one. So, summation n is running from 1 to infinity delta omega sin omega n x and then the integral minus infinity to plus infinity Ft sin omega n t dt. Now, we will use the definition of integral. You do remember that the definition of integral, this we are changing it to be, that is, since L is approaching to infinity, delta omega would be approaching to 0, omega n now we will take is approaching to omega. Hence, by definition of the integral we would get f x as 1 upon pi, this summation is changing to the integral 0 to infinity cos omega x. This is the multiple of this thing. So, what we are saying is now total function, this function is fixed with respect to now our limit, but one thing we are taking is omega n is approaching to omega. So, we are including it here that this function is changing to integral f t cos omega t dt, this integral. So, now we are getting finally 0 to infinity cos omega x into integral minus infinity to plus infinity f t cos omega t dt whole integral with respect to omega. Similarly, the second one, integral 0 to infinity sin omega x multiplied with integral minus infinity to plus infinity f t sin omega t dt d omega. Now, rewrite it again, assume a omega as 1 upon pi integral minus infinity to plus infinity f t cos omega t dt. This thing we are assuming as a omega, and because this would be a function of omega, t would be integrated out. Similarly, the other one we can assume as b omega, that 1 upon pi integral f t sin omega t dt on the whole real line minus infinity to plus infinity. Then rewrite the function, then f x we could write 1 upon pi integral, this integral again I am this rewriting. So, now this inside integral, this we are changing, this is a function of omega. So, a omega, and this inside integral is b omega. So, what we would get it rewrite 1 upon pi 0 to infinity a omega cos omega x plus b omega sin omega x integrated with respect to omega. This is called the representation of this function f x as Fourier integral. Why we are using the term Fourier? If you do remember, Fourier series we said is series of sine and cosine. Here what I am having is, I am having an integral which has cosine term and sine term, and it has certain coefficients which we call a omega and b omega. In the series, we, if you do remember, we were having its a n and b n and then the summation. Here we are having integral and this a omega, b omega, d omega. So, we are calling it Fourier integral. What it helps? Let us see this result which we have, find it out theoretically what it says. If f x is a piecewise continuous function in every finite interval and has a right hand derivative and left hand derivative at every point. So, now we are not assuming that the function is differentiable, actually we say is that is only if the left hand derivative and right hand derivative are existing and the function is piecewise continuous. Moreover, if the integral as a approaches to minus infinity of a to 0 f x dx and b approaches to plus infinity 0 to sorry it should be 0 to b mod f x dx, this must exist. This we can rewrite as integral minus infinity to plus infinity mod f x dx does exist. If you do have remember it, this is called the existence of integral of the function f x, or this is simple terms we say is that the function is integrable. Then f x can be represented by the Fourier integral as a omega cos omega x plus b omega sin omega x integrated with respect to omega in the interval 0 to infinity. So, what we have got, the function is, now we are not requiring the function to be your periodic, we are saying is function is piecewise continuous, has left hand and right hand derivative at every point, and the function is integrable on the whole real line. Then it can be represented as a Fourier integral. The form of the Fourier integral is that integral from 0 to infinity a omega cos omega x plus b omega sin omega x d omega, where this a omega is nothing but 1 upon pi integral minus infinity to plus infinity f x cos omega x dx, and b omega is the integral 1 upon pi integral minus infinity to plus infinity f(x) sin omega x dx. Moreover, at every point of discontinuity, the value of the Fourier integral equals to the average of the left hand limit and the right hand limit. This should be x plus 0 rather than f. F of x minus 0, that means the left hand limit at x, and f of x plus 0, that is the right hand limit at x. So, at the point of continuity we are having is that the can be represented, the value of the function would be equal to that Fourier integral, and at the point of discontinuity the value of the Fourier integral would be equal to the average of the right hand and left hand limit. Let us see in an example. Find the Fourier integral representation of the function 1, which is 1 in the interval minus 1 to plus 1 and 0 outside, that is this we are just having the same function. That says we want this kind of representation. We want an integral which has the terms a omega cos omega x, b omega sin omega x. So, we have to find out what is this a omega and b omega. If we can find out for this function f x, we could write it as a function. So, let us see a omega what it should be. Just now we had find out the formula, that 1 upon pi minus infinity to plus infinity f x cos omega x dx. Now, for this function f x, let us evaluate it. So, it should be 1 upon pi minus 1 to plus 1 cos omega x dx. This is an even function, sin omega x upon pi omega. So, we get 2 sin omega upon pi omega. This is what is my a omega. Now, b omega would be 1 upon pi integral minus infinity to plus infinity f x sin omega x dx. Evaluate it, minus 1 to plus 1 sin omega x dx, the integral is cos omega x upon pi omega, minus 1 to plus 1, this is 0. We need not to evaluate, we could have seen it, that is an odd function in the interval minus 1 to plus 1, so it should be 0. So, what we are getting is f x as 2 upon pi 0 to infinity. This is what a omega we have got, 2 sin omega upon pi omega, sin omega upon omega cos omega x d omega. This is the Fourier representation of the function f x. The theorem says that all the point of continuities, the value of the function at that point would be same as the value of this integral, and at the point of discontinuity it would be the left hand and average of left hand and right hand limit. The function, if you remember, we were having is 1 in the interval minus 1 to plus 1 and 0 otherwise. So, at both the points minus 1 and plus 1, the function is discontinuous. Let us see at point x is equal to 1, the function is discontinuous. So, the left hand limit and the right hand limit, 1 minus 0 means we are reaching towards from the left to the 1, that is the function is 1. So, that would be 1, and from the right if I reach it would be 0. So, it would be simply 1 by 2, and what is this integral value, that is the right hand side, this integral we are saying is that this function we are representing by this Fourier integral. What it would be? It would be nothing but 2 upon pi sin omega cos omega x over omega d omega. So, now I want x is equal to 1. So, what it would be? It should be equal to half. Now, let us write it out. It says is integral 0 to infinity sin omega cos omega, because at x is equal to 1 it should be equal to half. This is what the theorem is saying. So, integral 0 to infinity sin omega cos omega upon omega d omega, this we could write as, you see, pi by 4, because this 2 would come over here. So, what we have done is we have actually used the theorem which says is that if the function is piecewise continuous, we can represent the function by Fourier integral, and from there actually this function, this integral of this function, we had find it out. This was the point of discontinuity. Let us take the point 0. At the point 0 the function is continuous and f at 0 is 1. So, by the theorem we say is that this integral should be equal to the value of the function. So, what is this integral at x is equal to 0? If x is equal to 0, this cos omega x I would have as 1. So, this integral would be 2 upon pi sine omega upon omega d omega, and by the result of theorem it should be same as the value of the function. Value of the function at 0 is 1, so it should be equal to 1, or we can say that the integral 0 to infinity sine omega upon omega d omega is pi by 2. So, we had you would have used these integrals actually at many places in practical problems. So, we are finding out these integrals with the help of that theorem, which we are calling the Fourier representation of any function as a Fourier integral. Let us see cosine and sine integral, because just now in the example we had seen that we had got only the cosine term, not the sine term. So, when it will happen, as in the case of Fourier series, we had find out that if the function is even, we were getting only cosine series; if the function was odd, we were getting only sine series. Similarly, here the things will happen. So, we say if the function is even or odd, if function is odd, then f x cos omega x is also odd, because the product of odd and even function is odd, and f x into sine omega x odd multiplied with an odd function. So, product of an odd and odd function is even. So, f x sine omega x would be even. What it says is, if the function is odd and the a omega is 1 upon pi minus infinity to plus infinity f x cos omega x dx. This will always be 0, because the integral is from minus infinity to plus infinity. Remember that in the definite integral property we were having is actually minus a to plus a. Here we are taking it minus infinity to plus infinity. So, we are taking it as a limit point, and we are assuming that all those integrals are existing, that is why we are taking it to be 0. And b omega is 2 upon pi 0 to infinity f x sine omega x dx, because f x sine omega x is even. So, we can write it as 2 times that integral. So, 1 upon pi integral minus infinity to plus infinity f x sine omega x dx would be nothing but 2 times 1 upon pi. So, this is b omega, and what we will get? We will get only sine integral. So, f x would be only integral 0 to infinity b omega sine omega x d omega, where b omega is this one. This is Fourier sine integral. Now, if the function is even, what it says is f x cos omega x would be even, because the product of even function with an even function will give me even function, and product of even function with odd function, sine omega x an odd function. So, f x sine omega x, this would be odd. That says is, when we calculate this a omega and b omega, a omega the function is even. So, it would be 2 times 0 to infinity f x cos omega x dx. When it is odd, then b omega would be simply 0. It should be minus infinity to plus infinity. Thus, I can represent f x as 0 to infinity a omega cos omega x d omega, only cosine integral. So, as in the case of Fourier sine series and cosine series we have sine, here also we are finding out if the function is even, we get only Fourier cosine integral, and if the function is odd, we get only Fourier sine integral. Now, where we are using, so use of this Fourier integrals in evaluation of integrals. We had seen one example where we had integrated certain functions which we were not able to integrate as such. Let us see one example. Find the Fourier cosine and sine integral for the function e to the power minus kx for x positive and k positive. Let us try it. A omega, the function e to the power minus kx for x positive and k positive. So, we are having this minus infinity to plus infinity. So, we should start this 0 to infinity, because the function from minus infinity to 0 is 0. So, it is 2 upon pi 0 sorry, we want cosine integral. So, 2 upon pi 0 to infinity e to the power minus kx cos omega x dx. Integrate this one, we get 2 upon pi minus 1 upon k e to the power minus kx. This is integration by part. This function we are taking as integrating function, this as the differentiation function. Cos omega x 0 to infinity minus omega by k integral 0 to infinity e to the power minus kx sin omega x dx, which is 2 upon pi, simplification 1 upon k minus omega square upon k square integral 0 to infinity e to the power minus kx cos omega x dx. Now you see, this is what omega was, if I just remove this constant over here, just see that what is the integrand, e to the power minus kx sin cos omega x. Here also we are getting is e to the power minus kx cos omega x. The coefficient 2 upon pi, that is also here. What it says is, I have again came to the same kind of integral. What it says now, I take this integral 2 upon pi, that is it is omega square upon k square times a omega. So, what we are getting is 1 plus omega square upon k square times a omega is equal to 2 upon pi into 1 upon k. What it says, a omega is 2 upon pi k upon k square upon omega square. Now, you see, we were not able to calculate that integral e to the power minus kx sin omega x dx directly. We had calculated it using this recurrence relation, you could say. Similarly, so Fourier cosine integral of this function e to the power minus kx, we could write 2k upon pi integral 0 to infinity cos omega x upon k square d omega. Why? A omega cos omega x d omega. So, a omega is 2k upon pi times k square plus omega square. So, pi is here, k square plus omega square inside, because the integral is with respect to omega. E to the power minus kx fx is 2k upon pi integral 0 to infinity cos omega x upon k square plus omega square d omega for x positive and k positive. From here what we are getting? We are getting that integral 0 to infinity cos omega x upon k square omega square d omega is equal to pi upon 2k times e to the power minus kx. So, we are evaluating this integral with the help of this Fourier cosine integral. So, now let us move to the Fourier sine integral. So, for this we require b omega. What is the formula for b omega? 2 upon pi integral 0 to infinity fx sin omega x dx. Now, my fx is e to the power minus kx. So, we are having is 2 upon pi integral 0 to infinity e to the power minus kx sin omega x dx. Let us evaluate this integral by parts. So, b omega is this integral, we are going to evaluate it by parts. We will take e to the power minus kx as the integrating function and sin omega x as the differentiating function. So, first integral minus 1 upon k e to the power minus kx sin omega x evaluated from 0 to infinity minus omega by k integral 0 to infinity e to the power minus kx cos omega x dx. Now, when we are evaluating it, we put x as approaching to infinity, e to the power minus kx would approach to 0. So, this value would be 0. At 0 sin omega x, that is sin 0 would be 0. So, this would give us 0, and what is being left is 2 upon pi omega by k minus 1 by k integral, this again evaluating by the parts, e to the power minus kx cos omega x evaluated from 0 to infinity plus omega by k integral 0 to infinity e to the power minus kx sin omega x. Now, you see, we had again came to the same integrands, which was in the b omega. The coefficient is 2 upon pi is outside. So, we can again take this as b omega. Let us evaluate this function. As x approaches to plus infinity, e to the power minus kx will approach to 0, and as x approaches, x is 0, cos 0 is 1, e to the power minus k 0, that is this is also 1. So, what we are getting is 2 upon pi omega upon k square minus omega upon k square 0 to infinity e to the power minus kx sin omega x dx. This integral with 2 upon pi is b omega. So, we can get it as 1 plus omega square upon k square b omega is equal to 2 omega upon pi k square. This says is b omega is 2 omega upon pi k square plus omega square. Thus, what we are getting f(x), which is same as e to the power minus kx, that can be represented as a Fourier sine integral 0 to infinity 2 omega upon pi times k square plus omega square sine omega x d omega. And from here what we are getting is 2 upon pi omega sine omega x upon k square plus omega square d omega. So, this integral is equal to pi by 2 times e to the power minus kx, again for x positive and k positive. So, we had evaluated this integral with the help of Fourier sine integral. These two integrals just now which we had evaluated, they are called actually Laplace integral. So, what we are calling Laplace integrals? The integral 0 to infinity cos omega x upon k square plus omega square is equal to pi by 2 k for into e to the power minus kx, and integral 0 to infinity omega sine omega x upon k square plus omega square d omega is equal to pi by 2 e to the power minus kx. Both these integral are valid for x positive and k positive. These are known as Laplace integrals. So, we had seen that Fourier integral, Fourier sine and cosine integrals, and we had used them for evaluation of certain integrals. Now, let us move to the today's topic, that is the transform, Fourier transform we are saying. Now, before moving to the Fourier transform, let us first move to the Fourier cosine and sine transforms. What is the transform? An integral transform is a transform that produces a new function from a given function, and new function depends on the different variable and appear in the form of integral. You had already done one transform called the Laplace transform. Here we are moving to this Fourier cosine and sine transform. So, first let us see Fourier cosine transform. We want the function should be represented as the integral of something, and that should come out to be as another function in another variable. So, f(x) we do know by Fourier integral can be given as 0 to infinity integral 0 to infinity a omega cos omega x d omega when f(x) is even. Now, with a omega as 2 upon pi 0 to infinity f(x) cos omega x dx. This a omega, now you see we have got for this function f(x) we have got one integral which is again a function in some other variable. This we are calling Fourier cosine transform a omega, and moreover what we are getting is, if I again integrate this a omega with multiplication with this function cos omega x d omega with respect to omega, we would get back my function f(x). So, this a omega, this is called the Fourier cosine transform of f(x), and f(x) as integral 0 to infinity fc omega cos omega x d omega. This fc is not this capital Fc, this is actually this fc hat omega is the inverse Fourier cosine transform. So, what we are getting is, in you had read this you have already done this Laplace transform. In the Laplace transform you had not find out what is the inverse Laplace transform. Inverse Laplace transform you had find out, that is if a function is a Laplace transform of this function, then that function you call the inverse Laplace transform of the new function. But here we do have a formula, that is given this function, this Fourier cosine transform, without knowing that is from which function we had obtained this function, we could get the inverse Fourier cosine transform, that is again a transform in the true definition of the transform. So, another variant is here in transform I had used, that is cosine transform, I had used the coefficient 2 upon pi, this constant, and the inverse Fourier transform I have not used any coefficient, but some variant is, that is both the places the coefficient is being used as square root 2 upon pi. That does not matter in practical application, either you use this constant at both the places, that is in the cosine transform and the inverse cosine transform, or you use only 2 upon pi in the cosine transform and do not use any coefficient in the inverse transform. Similarly, Fourier sine transform is been obtained using the Fourier sine integral 0 to infinity b omega sin omega x d omega, where b omega is nothing but integral 0 to infinity f x sin omega x dx. This is Fourier sine transform of f x, and we would denote it by f s hat omega and write 2 upon pi 0 to infinity f x sin omega x dx, and f x, which is now b omega, I am writing it as f s hat omega, f s hat omega sin omega x d omega. This is inverse Fourier sine transform. So, one function we have got in omega from the function in x, then function in omega I was having, and I got the function in x. So, both are the transform, sine transform and inverse Fourier sine transform. Let us see some examples of these kind of. As I said, is sometimes this constant differ. So, let me just write it out that these constants. In my definitions, I had used 2 upon pi in the transforms and I have not used any coefficient in the inverse transform. Sometimes both the places this coefficient is square root 2 upon pi is being used, so that similarity can be maintained. So, we do get f c hat omega, that is the Fourier cosine transform, as square root 2 upon pi integral 0 to infinity f x cos omega x dx, and inverse Fourier cosine transform as f x as square root 2 upon pi 0 to infinity f c hat omega cos omega x d omega. Similarly, for sine transform, square root 2 upon pi 0 to infinity f x sin omega x dx, and in inverse Fourier transform, again the coefficient square root 2 upon pi integral 0 to infinity f s hat omega sin omega x d omega. Come to the example. Find the Fourier sine transform and Fourier cosine transform for the function which is 1 in the interval 0 to 1, minus 1 in the interval 1 to 2, and 0 for x greater than 2. So, now find out the transform. First, Fourier cosine transform. I am using the formula where the coefficient I am using as 2 upon pi. So, f c hat omega would be 2 upon pi integral 0 to infinity f x cos omega x dx. Now, f x is this function which is for which we have to calculate. This says is f c omega, f c hat omega would be 2 upon pi integral 0 to 1, the function is 1. So, 1 times that is cos omega x dx, and in the interval 1 to 2 it is minus 1. So, minus sign I have taken outside, it should be 1 to 2, not 0 to 2, it should be 1 to 2, 1 to 2 cos omega x dx. Now, evaluate these integrals. 2 upon pi omega sin omega, because integral of cos omega x is sin omega x upon omega, evaluated 0 to 1, minus sin omega x, evaluated 1 to 2, this omega we have taken outside. We get sin omega, sin x is 0, that is 0, sin 2 omega plus sin omega. It says is 2 upon pi omega times 2 sin omega minus sin 2 omega. This is what is my Fourier cosine transform. Now, find out Fourier sine transform. Again I would use the coefficient 2 upon pi. So, 2 upon pi integral 0 to infinity f x sin omega x dx. So, put the function is function is 1 in 0 to 1 and minus 1 in 1 to 2. So, break this integral 0 to 1 sin omega x dx minus integral 1 to 2 sin omega x dx. It is 0 elsewhere. So, we are assuming that the integral of 0 function is always 0. Evaluate this integral. integral of sine omega x is minus cos omega x upon omega. Both the places I am having the integrand as sine omega x, so omega just write it right outside, minus cosine omega x evaluated 0 to 1 plus sine omega x evaluated from 1 to 2. Now evaluate it, 2 upon pi omega, cos first it is minus sign, so first I am taking 0, cos 0 is 1, at x is equal to 1 it is minus cos omega, then cos 2 omega minus cos omega. So what we have got finally, 2 upon pi omega 1 minus 2 cos omega plus cos 2 omega. This is what is our Fourier sine transform of the given function. We can simplify a little bit more. Cos 2 omega we can write as 2 cos square omega minus 1. So we get 1 minus 2 cos omega plus 2 cos square omega minus 1. We could write it as 4 cos omega upon pi omega cos omega minus 1, simplified it, that is all. So we are getting this as the Fourier sine transform of the given function. So today we had to learn how to represent any function which is not periodic as Fourier integral, or we said is that is representation of a function as a Fourier integral. Then we had learned that is depending upon the property of the function, that is the function is odd or even, we can find it out whether it is, or we can represent it as a Fourier sine integral or Fourier cosine integral, and we can find out the transform. Then we had came to the transform and we had learned the Fourier sine transform and cosine transform. What is the use of this representation of function as integral or these transforms? For integrals we had used it for evaluation of certain integrals which as such we were not able to evaluate. Fourier transforms, we had started with cosine and sine transform. Our next lecture we will continue with it and we will see some properties and then we will move to the Fourier transforms. So that is all for today's lecture. Thank you.